the participants to this online class dedicated to Semester 6 Electronics and Communication Engineering students. Today's class instructor will be Jayakrishnan Divakaran sir. He holds a BTech degree in Electronics and Communication from College of Engineering Trivandrum and MS degree in Software Systems from 𝐓𝐢𝐦𝐞. He has attended the Master of Business Laws program from National Law School, Bangalore, and other continuing education programs from IISc and MIT Soleil. He has more than 35 years of product development experience, especially real-time embedded software in the defense, telecom, industrial, healthcare, and automotive verticals in varied capacities as developer, design lead, system architect, consultant, and director R&D. He is currently Vice President Engineering at a high-tech startup, 𝐕𝐸 Systems LLP Limited Liability Partnership Company. Before co-founding 𝐕𝐸 Systems, he was with Philips Innovation Campus, Bengaluru, leading the global product systems team for their flagship radiology informatics solution. He has led many successful national and international projects working in Bharat Electronics and Tech Mahindra. Apart from teaching at CET Trivandrum and GEC Kannur as a visiting faculty while on sabbatical. His current areas of expertise include innovative product development, human-centered design, cyber physical systems, 5G edge computing, data analytics and machine learning, deep learning applications as well. On behalf of ASAP and ASCC division, I welcome you, sir, to deliver today's class. And on this note, I would like to welcome all the attendees to the session. Let me conclude this introductory part by giving the outline of today's class. The entire 1 hour class will be divided into 2 continuous sessions, and each session will have 20 minutes of lecture and 10 minutes of question and answer interaction respectively. And during the interaction time, students may use the question and answer window or chat window to raise their questions. All the students are requested to maintain a classroom decorum throughout the session. Jayakrishnan sir will be available online throughout the entire 1 hour session. Sir, you may please start the session.
For inviting me to this session, and good afternoon to all the participants for this session. So we will start on the exciting world of embedded systems, and we are going to focus specifically on module 6 of the S6 curriculum, which is of the university. Abdul Kalam University. So we are going to talk about auto. So you would have seen a interesting vehicle on the front of my presentation. This is the Mars Curiosity, robotic vehicle which landed in the Mars in 2012. It basically uses an autos, specifically VxWorks autos. So this shows even very complicated systems can typically be architected. Applications can be architected on top of real-time operating systems. So Wikipedia basically says a real-time operating system is a multitasking operating system intended for real-time application. So we will understand what is operating system and what is real-time, and we'll try to put the pieces together as we proceed. As students, you would have gone through most of the other modules, and you understand where and all embedded systems are used. Embedded systems are used in a variety of industries, whether it is consumer industry, or it's industrial application, or military or defense application. You can see every product around has got a microprocessor and an embedded software embedded into that. So you can see whether it's a kitchen, or whether you are living room, or whether you are in the office. You can see variety of products here where it goes. So I will walk you through quickly the various portions in your module 6. Module 6, as you know, is the last module in your embedded system course. So I will do a quick refresher in case some of you have missed some of the in-between modules, so that you will get a better foundation before we dive into the other complex areas. So let me give you a caution to you. This module 6 typically is taught in an 8-hour multiple sessions. So what you are going to hear today is going to be a overview of things. So you need to really do a lot of homework by yourself, going through textbooks and going through sections in detail, basically for you to attempt the exam. So don't think this is going to be a very comprehensive this thing. As I told the syllabus calls for 8-hour session. So we are trying to see, how best, we can do an online, session where you will be given some high level, overview. So basically, I'm saying that this is not a substitute, for the classroom sessions, but this will give you, a high level overview, which will trigger your interest, in this domain to read textbooks and, understand, more details, and then, do a good job, in designing projects at the same time, doing your exams. Let me give again one more caution that I will not be talking in detail on Micro C OS2 because it's a special RTOS where a lot of system calls are being discussed in your textbook. So to ensure that I cover everything in time, I am just keeping it separately. But generic aspect of the operating system, the concepts, foundations, everything I will be covering as we proceed. And I will also, highlight, some of the popular real-time operating systems, and then, where it is used, and things like that. So I will give you an industry perspective at the same time. The foundation aspects, I will be covering, in the next 1 hour. So let me quickly, take you through, the highlights of, an embedded system. So unlike, a general purpose computing, environment like, a laptop or a desktop, computer, embedded system is peculiar. What is peculiar there? Because embedded system, you can think like an ant. But whereas, the general purpose computing systems like laptops and, desktop system can be taken as, a host. So you can understand, how much, constraints are there in an embedded system. Because embedded system, a typical embedded system, as you know, it consists of, a microprocessor, microcontroller, typically integrated inside a system on chip. And there is memory, because memory why is required, because all your program and your data gets stored in these memories. And then you have got different peripheral IOs. You would have gone through different types of IOs by now. And there are communication transceivers to connect with other embedded systems. And typically embedded systems will have sensors and actuators for various purposes. Sensors like temperature, pressure, and things like that. When you talk about actuators, it could be solenoid valves, motors, different types of motors like BLDC motors and things like that. And there will be power converters. Embedded systems typically work on batteries. And then you will have either RTOS need not be there in an embedded system, because simple embedded systems like a washing machine or a rice cooker, it doesn't need a complex RTOS there. So even with a simple executive, which I will explain later, you will be able to write a software and make it provide the services that you want. But complex embedded systems, you need to have an RTOS so that application development becomes simpler. And all these things are typically kept in a ROM, by embedded ROM like a flash or that sort of storage. That's why it is called an embedded system. We are trying to embed your application programs in a semiconductor device like a flash memory and things like that. That's why it's called embedded system. Unlike these large computing systems, laptops and all, we know that there are 4 CPUs which all run at 4 gigahertz, and there's got a lot of RAM and things like that. Microcontrollers typically run at lower frequencies, and its memory footprints are all like kilobytes and a few kilobytes, things like that. It is so that's what I told. It is like an ant compared to a general purpose computing platform, which is like a host. So the difference in the performance between the two. But unlike general purpose computing systems, embedded systems don't need to work 24/7 by 365. And many of these embedded systems are kept in large towers and other places where you cannot send a human being to reset. Suppose if it hangs. But suppose your PC, laptop hangs, what you do, you just reset and, it will again, restart. But embedded system, is not under your command. It is somewhere, in remote areas and harsh environments where, you will not be able to, reset the microprocessor. So everything has to happen automatically. That's why it has to work, 24/7 by 365. So it need to have, high quality, reliability, availability, safety. These are all, some of the properties of embedded systems. And then embedded systems are designed with the constraint of cost. Suppose a laptop costs 30,000 rupees, you can see an embedded system which costs 200 rupees, 300 rupees. So cost is a significant aspect in designing embedded systems. And the power consumption, you cannot many times connect to a AC mains where you can draw a lot of power. Embedded systems may have to work on button cells and small batteries for many years without replacement. So power consumption is a major issue. Then it need to be compact and all those things, and it has to work on extremes of temperature, pressure, and various harsh conditions. So you can see on the right side, a lot of embedded platforms here, which many of you are familiar, starting from Arduino, then Raspberry Pi, and you can have ST micros, boards, Texas Instruments boards, and then even the latest artificial intelligence, data, machine learning and data deep learning, can be executed on the NVIDIA, Jetson Nano, board that you are seeing below. These are all embedded systems. Depending upon what you want to achieve, depending upon the processing capabilities that you need, you can choose one of these boards. Starting from the 300 rupees, 400 rupees in Arduino, going up to that $99. The Jetson Nano, from NVIDIA for implementing your programs. This slide basically talks about an architecture of one of the embedded platform. So where you can run very interesting embedded application. This is a Raspberry Pi. You are all familiar. Currently, version 4 is running now. Very powerful platform. And these are all based on SoCs. So system on chip is nothing but an integration of CPU along with a lot of peripherals. So it is like the puzzles which you all play with. Semiconductor designers basically package multiple peripherals like what you can see on the extreme right and bottom. And then they make SoCs. So SoCs gets embedded on printed circuit boards like this, and to make printed circuit assemblies, and then you get powerful platforms like Raspberry Pi. As you know, Raspberry Pi is based on an ARM processor, and you can see the resources here. You can see Wi-Fi, you can see Ethernet, you can see USB, and then all these things are connected through various interfaces. Which you have studied in module 2. So I won't spend much time. I just wanted to give you a feeling of the overall architecture of an embedded platform based on whatever concepts on interfacing that you learned. This is just to highlight the various ARM processors which are typically used in embedded systems. And as per your syllabus, you study about ARM 90 DMI. That's the processor. And then it is based on ARM architecture called ARM version 4. So many students typically get confused that the processor that you are studying is the latest, but it's not latest. It is ARM version 4. That is the architecture version. But then the chip is called ARM 90 DMI. Which is typically used in your lab and everything so that. But there are a lot of high-end architectures which has evolved now. We are now currently in version 8, and I don't know whether version 9 has come. And then there are a lot of processors called there is a family of processors called Cortex processors which use ARM as the basic core for implementing functionality. So one of the things which I highlighted here is a widely used processor in a lot of embedded systems nowadays. It's a very cheap and a lot of functionality gets embedded in this. So I just wanted to this. So I wanted to show you one of the example of an embedded system, because in your syllabus you study about 3 examples. One is mobile phone, the other one is a set-top box, and the third one is an ATM system. So these are all 3 embedded systems that you are learning. But if you really look at a mobile phone, we cannot say it's an embedded system, because just like a laptop, a mobile phone also has become very powerful. It runs a lot of applications. So it is not a custom application that is running on a mobile phone. There can be a lot of general purpose applications which can run. So from that point of view, I don't think a mobile phone can be considered as what you call embedded system. But set-top box can be considered, because it is for a specific purpose of getting video decoding and showing on a TV. So it's a custom application there. So set-top box is correct, and even the ATM machine is designed for a specific purpose. So we can say it's an embedded system for a specific purpose. But whereas mobile phone is like almost like a general purpose computing platform, like a laptop or anything, because you can run a variety of applications. And today's mobile phones has got 4-core CPUs and so much of gigabytes of RAM and all. It mimics almost like a computer. But I wanted to introduce you to one example called digital energy meter. Everybody will have an electric connection at your home, and then this product is there at the entry of your home. So this is a very interesting example for an embedded system, because you can see a microcontroller here, which is typically Texas Instruments makes some of the microcontrollers for here, like that. Renesas, and there are different companies who make cost-effective microcontrollers for this application. So it has got a CPU inside, and you can see various buses there. So one bus inside that microcontroller is called SPI, which you have studied, I2C, two-way bus, and then UART interface. All these things you studied as part of module 2. And then it has got RAM, it has got static RAM, basically for storing your data variables. And it has got flash memory, basically which stores your program, the code that you write, and the constants that you declared in your program. All those things get stored in the flash because it has to be in a non-volatile storage, persistent storage. Otherwise, it will go off when you switch the power off. And then you can see, a lot of devices here, getting hooked out to the I2C bus, and you have learned it as a two-way bus. And it is these buses are all inter-chip buses. There are two types of buses you have studied in your course. One is the buses which are used for connecting chips within a printed circuit assembly, and the buses which are used for connecting two systems. So I2C bus is an inter-chip communication bus which is used within the PCB, and you can see a variety of devices getting interface here. One is LCD driver, because this the meter has got a display, so it is interfaced through an I2C bus. So that is LCD driver stuff. And then you have got the RTC there, which is the real-time clock, which is typical of all the embedded systems. Because even when the main power goes, the time should not get corrupted. The time should keep on continuing, it should keep on ticking. So there is going to be a battery connected to that RTC, so it will continue to work even when the whole product doesn't work. And then the configuration information of this meter gets stored in a non-volatile storage called D2 form. So typically, these meters, after they manufacture, they have to undergo some calibration. And once you do the calibration, because these are all digital meters, the calibration values need to be stored in some device, a non-volatile device. So that's where this D2 form gets application there. And then you can see the UART there, which is typically the TXT RXT type of interface. They get connected to some of the optical and other type of transducers for reading this meter. And then you can see here an ADC here, because the external world in many of the embedded system application is analog in nature. But whereas embedded system per se is digital in nature, so there has to be a conversion from analog to digital. So that is accomplished by ADC, and you also learned about ADCs in your previous class and things like that. For example, in this meter application, you need to sense the voltage and you need to sense the current, which is going through these lines, and then voltage into current, and then you incorporate the power factor by looking at the phase between the voltage and current waveform, and then you will be able to compute the unit of power that you consume in an energy meter. And then for making all these devices work, you need to have a power converter which has to draw the energy from the main line itself. So in my view, a digital energy meter, which all of you are very familiar in the form, is a very good example of a typical embedded systems, which will which will make you think about all the things that you have learned in your curriculum so far. So let us now switch over to RTOS here. Real-time operating system. So what is real-time and what is operating system? Let us go to the second portion first, because many of you are familiar with what is an operating system. Operating system is a piece of code which is running on a computer, basically managing all the hardware and some of the lower level software resources. So the application program doesn't need to interact with the hardware directly, because if it interacts with hardware, there are a lot of challenges which will happen, which we will discuss later. Always operating system, application program uses the services the operating system basically to access the hardware features provided by an underlying target, and then so there are a lot of functions typically operating systems do. It enables you to do multitasking. It enables you to do input-output operations. There are timers, clocks, and memory management. There are a lot of functions a typical operating system provides. So instead of you reinventing the whole wheel, application programmer can focus on his specific problem, and he can write the code corresponding to that, and he can use the services of operating system which is written by specific companies like Microsoft has got Windows operating system. Linux is an open source community's operating system. Then VxWorks which I told used in the Mars rover project, that is written by that company. They are all experts in writing system software. So they have written this layer of software called operating system, and it provides application programming interface to applications, and then you can call you can use those application programming interfaces basically for achieving what you want to achieve in the application. That is the meaning of operating system. So then you may be wondering, now what is real time? Real time, so not all embedded systems need to have real time. For example, if it is an embedded system for your rice cooker, there is nothing like real time there. But suppose if you have an embedded system for a fighter jet which is flying at the speed of 2 to 3 times the speed of sound, then there whatever you use need to be a real time. That is because if the pilot applies a certain control, it need if he gives a stimuli, that means if he applies certain control, it has to the effect has to happen within a certain time. So if it doesn't happen, then the whole aircraft can, which is costing millions of dollars, can come down. So there are definite what we call time constraints which are put in for various stimuli in this sort of systems. That means once you invoke something within a certain time, few milliseconds, the action has to happen. If it doesn't happen, it will be a catastrophe. The platform itself will get it will malfunction and it will fall off. So there are two things in the case of real time. One is called logical correctness, and the other one is called temporal correctness. So temporal means in the time domain. Suppose we say something has to happen within 100 milliseconds after an action is done. Every time that stimuli happens within 100 milliseconds, it has to happen. 100 times if you do, if you say 99 times it is fine. One time it has become 150 milliseconds. That is not okay, because that one time is sufficient for a platform like an aircraft to come down, nose diving. So 100% of the time, that temporal correctness. That means, within that time that is stipulated, the action has to happen. And then the action also need to have, a logical correctness, which is typical of any, embedded systems. So both the logical correctness and temporal correctness need to happen, when we use, an RTOS in a particular platform. So what is an operating system? An operating system, if you see here, you can see a kernel here. It is like a fruit. Look at a mango, you can see, a central, a seed there, which is like a kernel. And then the flesh around, the kernel, that is what we normally eat. That provides a lot of support, like file system support. There are some networking protocol support. For example, many of the embedded systems has got a protocol stack called TCP/IP that enables the embedded system to connect to the external world. So the file systems, and then there are a lot of library supports it will provide, C++, and then debugging facility. All those things, around the kernel, we can say it's like a flesh. In the Unix terminology, it is called a shell. But in embedded system, we don't use the word shell. We use, all the services around the kernel. And then application is on the top. Application uses all the services provided by both the kernel at the same time. All these other services that you are seeing here. And kernel and other services basically connect to the target hardware through something called BSP. This is called board support package. Whichever organization is making the printed circuit assemblies like Raspberry Pi or an Arduino or any of those platforms, they provide BSPs. BSPs is nothing but a set of device drivers. Device drivers also you would have studied in the previous module, so I will not go into the details. Now let us look at the kernel. Kernel has got different services. So the first service is task management, because we will understand what is task later, and then we need to think about how to synchronize the task. When multiple tasks are there, we need to synchronize that, and there are a lot of timers in these systems because many things need to happen as per specific times. So there is something like a timer management, and there is input-output device, a lot of peripherals here which need to be managed, and then there is memory management. Because every task wants a lot of memory, but then there is limited memory in all these embedded systems. As I told, embedded system has got a lot of constraints. So memory footprint is one of the constraints. So memory need to be effectively managed. And then the concept of interrupts and event and all you have seen in the previous module. So I will not go into the detail. But these are the 6 different services the kernel does. Kernel is the core of an operating system, and then application uses these services for accomplishing various things. And as I told, around the kernel, like the flesh in a mango, you have a lot of other services like networking, file systems, and various things. Let me go to the other things. In an operating system, there are two, spaces. One is called, kernel space, and the other is called, user space. Most of the microprocessor on which this real-time operating system runs has got privilege modes. Unlike 8086 or 8085 and all, you studied, they don't have these specific modes to support RTOS. But from 286 onwards, and even the latest ARM processor, everybody has got privilege modes in the microprocessor. So that means for kernel, the microprocessor gives all privileges. So it can execute every instruction in the microprocessor. But user space, you will have only limited access to the microprocessor resources. And user space is the place where we run application programs. That is why in Unix and all the operating systems, application programmers, even if they screw up their code, the system will not crash. Because we run our application in the user space, and user space cannot access all aspects of the hardware because the specific features built into these microprocessors. But kernel code is typically written by system programmers, people with a lot of years of experience, 20, 30 years of experience. So the assumption is that they've done a very good job of this kernel code, so that it will not even if it touches some part of the. So the assumption is that they won't do unnecessary things in the microprocessor, because they understand the microprocessor very well. But they have been given full privilege to access all parts of the microprocessor. So that's called the kernel space. User space, only certain areas of the microprocessor features you cannot access. So all these things you studied in previous this. So now there are different types of kernels. One is called the monolithic kernel, microkernel, and SO kernel. We will not spend much time on this area. But typically, Linux and Windows, these are not used in embedded systems. They use this monolithic kernel. That means there are a lot of features you can see in the kernel space, file systems, I/O, all those things you can see on the kernel space. But whereas in an embedded system, RTOS, sort of environment, we use microkernel. That means a lot of the functions like file systems and all those things have been moved to the user space. And then the kernel is very, very small now, because a lot of features have been removed from the kernel and put in the user space. So this is typical of all the RTOS. Most of the RTOS use a microkernel, but whereas general purpose operating systems like Windows and Unix and all use a monolithic kernel. And then exokernel is a concept developed in MIT in their parallel and distributed lab, which will give the applications some privileged access to hardware through a mechanism of virtual files and things like that. So let us not go into the details of these areas, but just understand our RTOS typically uses a kernel called microkernel, where the kernel has got very limited functions, and all the other features like file systems and communication interfaces, many of those things are moved and put in the user space. Why RTOS for embedded systems? So there is no, as I told earlier, simpler systems. There is no need for an RTOS. Like a rice cooker, it doesn't need an RTOS. But when the system becomes more complex, if we use an RTOS, the application development and its performance tuning becomes much simpler, as we see going forward. So that's what with respect to the embedded system system. So I won't spend much time here. So basically, I just wanted to say that RTOS is basically a layer of software which abstracts a lot of things from the user who is writing the programmer who is writing the application. His job becomes very simple. Without using RTOS, many of us have developed applications long back, but there we use a simple thing like there will be some initialization, and microprocessor is reset. There will be some initialization routines which will execute, and then there will be a while for our loop which will be continuously rotating and rotating, which will do multiple tasks based on some flags, and these flags will be set and reset by interrupt service routines. So that is how simple executives work. In a simple executive situation, as I said, there is no RTOS. There will be an initialization thread, and there will be a while for our loop. And within the while for our loop, there will be a lot of flag checking code. And then these flags will be set asynchronously by interrupt service routine, which will come when external events happen. That's how a simple executive based embedded system. But once RTOS comes into picture, then a lot of features we will get. We will have a very fine control on various processing which need to happen in the systems. So we'll understand how this is possible. So classification of RTOS, let us understand. There are three classifications with respect to response time. As I told, real-time operating system, real-time is very important. So there are applications like that fighter aircraft which I explained, where when some trigger happens, the action has to happen within a predefined time. If it doesn't happen, it will be catastrophic. So those systems are called hard real-time systems. So as you see here, a missed deadline here has got catastrophic results. But there are certain embedded systems. What is happening is even if rarely if it happens, it is okay. But then missing a deadline might result in an unacceptable quality reduction. That is okay, but then it doesn't result in catastrophic results. Many other thing on the ground, you can think like that. Even if something happens, somebody some alarm can happen, and people can work on restoring the service and things like that. And then there are soft real-time systems. An ATM machine is a typical example of a soft real-time system, because you are interacting with the screen using the keyboard. So sometimes you can see ATM machine becoming slow, and sometimes it is fast. So even if some of your transactions become slow, you are not really concerned. So that is not a big problem. But majority of the time we need good responses. Otherwise we will feel very bad about the product. But once in a while, when things become slow, we can tolerate. So those systems are called soft real-time systems. So our ATM machine is a typical example. But whereas hard real-time, a fighter aircraft, suppose it's braking or any of those systems, that can be considered as a hard real-time system. And you can find out a lot of systems on the ground, which can be in between these two. That is called firm real-time system. And as I told, a real-time system is a layer of software on top of a microprocessor architecture. So you can have a variety of processors starting from 8, 16, 32, 64-bit architectures. So depending upon the version, the type of architecture it supports, you can classify RTOS. And then based on the distribution also we can classify. Many of us, when we started our career 35 years back, that time, the RTOS was not much, in the industry. So we have even in-house, developed RTOS while I was working in Bharat Electronics. But then subsequently in the 90s and till now, there have been a lot of commercial real-time operating systems. In fact, there are 80 commercial real-time operating systems around the world which people use. And then there are open source operating systems also. In the last 20 years, open source is coming up in a big way. So there is an operating system called FreeRTOS, which is an open source. Currently, Amazon has picked it up, but still users can use open FreeRTOS in various applications. So this is the high-level classification. Yeah. So Anish, anytime you want to interrupt, you can interrupt for the Q&A session. But otherwise, I'll proceed fast.
Yes, sir.
So do you want to break here now for a Q&A?
Sir, as of now, I have received one question. So I would like to inquire the same. So the question is, can kernel keep state information about the use of input-output components?
Based on input-output components, that question is not very clear to me. Maybe we should take it up at the end, or we should take it offline, because that input-output component, it was not clear to me.
Okay, sir.
Okay, any other questions?
Continue the session. No, sir.
Yeah.
We can continue the session.
So let us understand the features of RTOS. As I told, multitasking. Okay, because as an application programmer, you can write a code in a monolithic fashion from top to bottom. But then it becomes very difficult for you to fine tune the performance of your application. So what typically people do is a long program, they will split into multiple tasks based on the functionality. So once you split into multiple tasks, it is like multiple threads. Multiple threads means they are not linearly going to execute. It is not going to be executing linearly. But then you can schedule based on some of the things that we are going to discuss now. And the preemptibility also, I will not discuss at this point. I will start showing it in some time domain charts, and then you will understand these things. But multitasking basically is instead of writing a monolithic, long program from top to bottom in a linear fashion, what you are trying to do is you are dividing it into multiple chunks so that they can be executed in parallel. So this concept of parallelism, that also I'm going to explain as we proceed. But then once you split a large application into multiple tasks, all these things are called tasks, and we have to give different priorities. Not all tasks in all these embedded systems are having the same priority. Some tasks will be high priority. For example, in the fighter aircraft case, when a pilot gives some braking command while he is landing, that priority of the task is the highest. But there could be some other actions on his cockpit displays which can happen very slowly. So those tasks you can give lower priority. So that means in any real-time embedded system, there need not be that all the tasks are having the same priority. There are some tasks which are very high priority and some tasks very low priority. So that is the beauty of embedded systems. In a monolithic case, everything has to execute with the same. Every portion of your code has to execute and the same priority. But once you divide it into multiple tasks, and once you run these tasks under a real-time operating system, we have the advantage of giving different priorities for different tasks. So high priority tasks, they will get more preference with respect to low priority tasks. So we will see all these things later. So a high priority task, I can say it is like a VIP. When a VIP arrives at a scene, you can see everybody goes towards the VIP. Nobody bothers about the common man. Okay, so even in our society, we can have we can see a lot of priorities among different strata of our society. So like that, in our applications also, we can have tasks of different priority, and then somebody has to schedule these tasks to the CPU, because the CPU is only one. I'm only talking about the case where the CPU is one, but if you really look at today's platforms, there could be multi-core CPUs. So the discussion there is completely different, which is not in the scope of your course for undergraduation. So let us in all the discussion going forward, we will only talk about a environment where there is only one CPU core, so that it has to be shared across multiple tasks. So how do you do that based on this priority? That is the beauty of real-time operating system. As I told, these once you have multiple tasks, it is not that these tasks will exist independent. So it is not like people don't talk to each other. Even in a team or a group, each of the individual will be doing a certain task. But in between, people need to talk to each other to get some input from the other person and things like that. Even in your combined studies, you keep doing that. It is not that one person studies everything. That's not what happens in academia. Many people together, each person will do their portion of the portion study, and then you will interact with each other and for various other things other person has studied. So there is going to be a lot of inter-task communication. So let us understand how all these things happen in a real-time embedded system. So there is something called priority inheritance, which is a very core topic, which typically takes a lot of time to explain. But let us park it here. Then we will talk about latencies. So there are two latencies in embedded system. One is called interrupt latency. Other latency is called task latency. So interrupt latency is like this. In a microprocessor, when we talk about interrupt latency, we have to just talk about microprocessor only. We will not talk about an operating system that time. So that means when an external event happens, within how much time the microprocessor responds to that external event is called an interrupt latency. So this depends upon disabling of the interrupt, how long interrupts are disabled in your code. Because as you know, in microprocessor, there are instructions to disable the interrupts and then enable the interrupts. So when you execute your program, certain portions of the program you want to protect. So you don't want the other person to interfere while you are executing this. So that time you will disable the interrupt, and then once you are done that critical task, critical section, then you will enable the interrupt. So in a microprocessor-based environment, the code which has disabled the interrupt for the maximum time, that code how much time it will take to execute, that decides the interrupt latency. So that means as a programmer, you should not disable interrupt for a long time, because interrupt is a feature in an embedded system which gets an immediate attention. So if you disable the interrupt, what will happen is even if the external interrupt comes, nothing happens on your system because system will not respond. So what you do is whenever you have to do some critical sections, what you do is you disable the interrupt, do that critical section, and then you enable it immediately, because otherwise external events will not be recognized by your embedded system. So that is called interrupt latency. But then when you come to the task level when we talk about, we have to bring in our operating system into picture. There what happens is, as I told, multiple tasks will have multiple priorities. So suppose a low priority task is executing in the CPU. Suddenly a high priority task happens because of some event which has happened in the external world. Then if you have disabled the interrupts for a long time, again you will not be able to respond to the high priority task. So there is this concept called task latency, which are typically in the order of microseconds, 10 microseconds and things like that in many of the RSS. But compared to an interrupt latency, which is talked at a microprocessor level, which is maybe a microsecond or something. Typically, a task latency, since it is coming under the umbrella of operating system, there are a lot of overheads in operating systems. So that will be many times compared to an interrupt latency. That is what we need to understand. So we'll go to the next one. So this is something which you should be familiar: process and thread. So let me explain the concept in simple terms. Suppose you work on a Linux machine or a Windows machine. You will have multiple applications on that machine. For example, there will be an email client running. There could be multimedia, YouTube, program you may be watching. There could be a word processing software will be running. So each of these applications, in a environment like Windows or Unix, we can call it as a process. The importance of process is that the process will have its own private memory. That means one process cannot screw up another process, because all these processes are typically written by application programmers like you and me. So even if you do a bad job in writing one application, it cannot crash another application. You would have seen it in Windows. Some applications they crash, but then it will not affect all other applications which are running, because they are all written as processes. Because processes will not share data and address space, and so they will not crash each other. They are independent portions of the code with their own code, data, and files and all sorts of things, as you see on the single thread which you are seeing there. And it has got something called process control block. I will not get into process control block because we are going to talk about real-time operating system, where the TCB is not a big concern. There we have got an equivalent thing called TCB, which is called task control block. So on the right side, you are seeing multiple threads there. So each of these threads is nothing but a task. But you can see there, there are a lot of sharing which happens across these threads. That's how a lot of communication between the tasks happens in real-time operating system scenario. But the thing is here is that if one's task, if you don't write it properly, and if it screws up another task, the whole system will crash. So that is the problem on the right side. But whereas on the left side, processes, various application programs, as I discussed in Windows and Linux environment, they run in its own address space. So they don't share things each other without through memory and things like that. But there are other ways of socket-based communication and all, by which you can share even in processes also. But then each of these processes run in a very independently, and it won't crash each other. But whereas the threads in a real-time operating system scenario, if you don't write it, and if you screw up another thread, then the whole system can crash. So this difference you should understand. So a thread is the unit of execution within a process. That means in a computer, a laptop or a desktop, there can be multiple programs. So each of the program, you can say it's a process. But then one process can have multiple threads. So that is called a task. So real-time operating systems, basically we talk about tasks. So going forward, I will not use the word process. I will not keep on using the word task. A process can have anywhere from just one thread or one task to many threads or many tasks. And so you can see on whatever. So now, what is a task? Okay, so let me introduce something called concurrency at this point. In all systems, we need to understand the concept of concurrency, because the CPU is only one, and then there are multiple tasks. So only one task can use the CPU at a time. Okay. But this is like, Vishwanathan Anand, playing chess, with, 50 people simultaneously. So Vishwanathan Anand is a CPU here. But each of you, with whom, he is playing chess, he is nothing but a task. But Vishwanathan Anand is so fast, and he is able to, make the movement so quickly. So he will go in a round robin fashion so quickly. By the time you think, he would have completed all the other 50s, movements, and then he will come back. This thing. So you can compare, a CPU to Vishwanathan Anand, and each of the tasks has, you people, playing, chess with you. So you get an appearance that that Vishwanathan Anand is dedicated to you. But that, like, in a real-time situation also, everybody will think, the CPU is always for your task. But since CPU is very fast, you will get a feeling that CPU is always dedicated for you, but it is not like that. CPU is, giving certain portions of the time, for different people, and they are doing. CPU is a very fast engine, so it is able to complete work for all the people. So we get the feeling that simultaneously you are able to use the CPU, but there is no simultaneous thing there, because one at a time only you can use CPUs. So that is the concept called concurrency. Concurrency means you get a virtual feeling of simultaneous execution, but then one at a time only execution happens only microprocessor. So in a task, you can see, there are different, things like task control block, task stack, task routines, and all. So every task, should have an ID. Typical, operating systems, has got 1 to 255, with 1 being the highest priority task ID, and 255, the lowest priority task ID. Then you can attach a priority. That means, suppose there are 5 tasks now, which are on the same level. I can give the same priority number to that. But task IDs will be different, because every task will have a unique ID. But then priority, can be the common across few, tasks. But the highest priority fellow will have a number which is much lower, and then other things can be this thing. And then in microprocessor, the concept of status registers, program counter, status pointer. See, all these things are part of tasks. Because all this information is very important when you switch between one task to the other. Because the information corresponding to the microprocessor status in the first task has to be stored when you move to the second task. And then after completing the execution, we should be able to, get back, this task control block for the first task, then you can start executing. So task control block, is very important. We will understand how the task control block works. So this is the task scheduling. So you can see, multiple, states here. This is like a state diagram. I don't know how many easy students are aware of this, but computer science students, typically learn, some technique called state transition. So I can put it in simple form here. There are multiple states here, and then you will traverse from one state to the other when certain system calls are done, in this real-time operating system scenario. So when a real-time system starts, all the tasks, suppose there are some 10 tasks in your system, everybody will first come into the dormant state. So that is the entry state. That is like a gateway, into the system. And then these tasks, I told 10 tasks, only one task can be going to the running task at a time. Okay. So before getting into the running task, a dormant task cannot directly go to a running task. First, it has to go to a ready state, and it has to be there in a queue. And then the operating system, depending upon your priority, because as I told, in a multitasking situation, there can be different priorities for different tasks. The highest priority task will be taken, and you will be pushed to the CPU. And then once he completes execution of his part of the code, then he can come again back to the dormant state. And then after a certain time, when you want to go into the running state, first you go to the ready state, and then depending upon the priority, it will be scheduled into the running state. But while you are executing as a high priority task into the CPU, the running state, suppose you want to get a resource, suppose a printer resource. And then you try to call and make a system call to get the printer resource, but some other task would have taken that resource earlier. So immediately you will go into the block mode, okay? And then some other lower priority task will come from the ready queue, and then it will go to the running state. So so that means in a real-time operating system scenario, what will happen is all the tasks will be in one of these states. And there can be only one task, in the running, state, because that is the one which is using the CPU. but there can be many tasks, in the ready queue. There can be many tasks in the block queue, and there can be many tasks in the dormant queue. And then all these transitions happen by inter-service routines, by system calls. Those are all the ways in which these transitions happen. So I will not complicate this at this point, except to say that the switching a task a task once a task is running in the CPU, switching to another task to come and use the CPU, that is called context switching. So let us understand what is this context switching now. So there are two types of scheduling by the real-time operating system. One is called non-preemptive scheduling, and the other one is called preemptive scheduling. So let us look at this non-preemptive scheduling. There are 4 tasks here. The first task got scheduled, and then it completed its job, and then task 2 was able to execute, but it has got a lower priority because the vertical axis is task priority. So task 2 is having low priority, so it executed, and then suddenly and then it completed. Okay, and then task 3 was taken and it was executed. It completed in time domain. The horizontal axis is the time, and then it went into task 4. Okay, and so no tasks are getting preempted. So no interruption is happening in any of the tasks. Each of the tasks it completes its execution, the portion of the code, and then the real-time operating system schedules the next task. So it's a very simple scheme here, non-preemptive scheduler. But look at the preemptive scheduler. Okay, the task 2, task 1 was executing here. Okay, and then it completed because that time no other high priority task was there. Task 1 completed as planned. But then task 2, a low priority task started getting executed. So you can see in the time domain it is executing. Suddenly, before the task 2 got completed, a task 3 is coming up now. Okay, and then in the earlier case, even if task 3 comes up also, unless you complete task 2, the CPU will not be given to task 3. But here, immediately, task 3, is given the CPU. That is called preemption. And then the high priority task 3 completes, and then again task 2, which didn't get completed, will continue completing. So that is what you are seeing there. So task 2 got divided now in time domain because of that task 3, which is not the case in the non-preemptive scheme. So hard real-time systems need a preemptive kernel. That means in hard real-time system, as I told, suppose some breaking event came. That will result in an interrupt service routine, and that interrupt service routine will schedule a new task like task 3, and immediately a task switch has to happen to task 3, because if you wait for task 2 to complete and then schedule task 3, what will happen is by the time the aircraft will be down. So we need to use preemptive scheduler in the case of real-time hard real-time systems, because you get instant response to high priority threats or high priority tasks. So that is what you are seeing there. But whereas non-preemptive is a very simple scheme. Debugging the code and all becomes simpler now when you talk about a non-preemptive scenario, because everything happens in some sort of a logical sequence. But whereas in the preemptive case, you can see switching happening without your knowledge. So when you debug your code and all, you get surprised while you are debugging in sequentially a task 2 code. Suddenly you see task 3 is getting debugged. So you get confused. Even hard real-time people, when they develop their program, first they will enable only non-preemptive, so that logically they can debug the program well, and then to enable this real-time response, they will again enable preemptive later, so that all the hard real-time constraints you'll be able to meet. So I have only hardly 5 minutes. So there are a lot of inter-task communication mechanisms. One is called message queue, mailbox, pipes, and remote procedure call. So remote procedure call, let me give you some idea, because others are simple, we understand. Suppose there are 2 embedded systems. Okay, so there are multiple functions in your application program for the first embedded system. So everything is running on the local CPU. But suppose the other embedded system provide you certain functions which is not there in your code. You can invoke that function from in a remote embedded system using this thing called RPC. So that means you make a call and the call go through some socket calls and all to the other embedded system, and it gets executed in the other embedded system, and then the results will come back to you to your embedded system. So this is called RPC. This is used in a distributed environment. But then message queues are between tasks. You can have a FIFO, LIFO, and priority based queues and things like that, so that you can talk to each other, task and talk to each other. Mailbox is nothing but a message queue with just one message at a time. So that's called mailbox. And the pipes are key for simple mechanisms, which are a subset of message queue. But then it is used for byte stream based communication. But whereas the other one message queue is for the concept of message need to be there during communication. So we also need to talk about semaphores. There are different types of semaphores which we'll see. So semaphore is required in embedded systems because there are certain few resources in an embedded system, and every part.
Sorry to interrupt you, sir. We are
yes
entering the last 5 minutes of the session. So
yeah, I think we have to conclude here. So there are binary semaphores, counting semaphores, and mutual exclusion semaphores. These are basically used for sharing resources in an embedded situation. These are good illustrations which you should be able to see it this thing. And as part of the course you study about other real-time operating system. And let me tell, 𝐓𝐸𝐸𝐻 is the most widely used real-time operating system currently. But there is open source free RTOS from Amazon which many of you can use, and there is RT Linux and other types of operating systems. But as I told there are some 80 operating systems in the market. So micro C OS2 what is you study in detail, I didn't include here. So you can go through the textbooks in that and understand the different function calls, system calls which are used in that list. So I will just stop at this point, and I have included some two important textbooks other than the two references which are given here. These are very simple textbooks which you can access online. There could be ebooks or PDFs. They have introduced all these concepts in a very simple manner, and there are a couple of application notes I have given here. That also you can refer, because a lot of text I have taken from some of these things. So this will help you to go through these areas much more deeply. So I'll stop at this point and I'll take the questions if any.
Okay, sir. So there was one question from Pranav Anandakumaran. He has asked how are tasks given priority, whether it is given through flags.
Could you again repeat?
How are tasks given priority, through flags?
Yes.
Is it given through the flags?
Yeah, so the last point I didn't get, but let me tell, in an operating system, as I told, typical operating systems support 1 to 255 priority. So while you architect your application, as I told, you will split up the application into multiple tasks, and then you will understand which are the tasks which need to have the highest priority. So you will give these priorities in a static manner while you design the application. But then even during execution of the application, you can change the priority of this task in runtime, basically to avoid some things like the priority inversion and things like that. But the designer, as part of designing the application, he understands which are the tasks which need to have high priority, and then in the configuration of the operating system in the beginning, you will set up the priority number for different tasks.
Okay, so that is clear. Another question is raised by Shyam Krishnan. He has asked, can Raspberry Pi run in any of the RTOS available today, like 𝐕xWorks or free RTOS?
What I understand is, as all of you know, Raspberry Pi runs Linux distributions, and then even Microsoft has put Windows 7 there. But then WindRiver, as I see, they have done porting on Raspberry Pi. But other vendors, whether they have put they have tested their RTOS on Raspberry Pi, we need to check. But I know 𝐕xWorks has application notes I have seen which they have done.
Okay, so that was clear. Another question is, how can we switch from user mode to kernel mode in RTOS?
Right. Yeah. So what happens is this happens when you do system calls. Okay, as I told you, there are two programs now in a system. One is called the application programs, which you and me write, and the other aspect is the operating system kernel and other things, which system program is write. So as I told, the interface between the application and the operating system kernel and those sections is through system calls. So when you do the system call, what will happen is from user mode, the processor switches to a kernel mode, where the kernel will be able to access all the features of the processor. But whereas in a user mode, it will have limitations. It cannot play with some critical registers of the microprocessor.
Okay, so that was clear. As we are nearing the end of the session, so I would like to conclude it by saying thank you, sir.